So, quick agenda. What I want to do, I want to. This is going to be a lot more about storytelling. Well, there are plenty of graphs and concepts, but be mostly about storytelling. A little bit about background and my personal experience with this. Sharing what we do, our mission and purpose, in order to create the outcomes that we've just been referring to. A couple of key principles, some case studies, and then some take homes to remember. So, background for me. Whilst I do run AZZO as a business, I am a chief geek. I love this stuff. I'm principal engineer and couldn't be more excited to be sharing, hopefully, what are technical things in a simple to understand way, I hope. Now, a little bit more about me. I live in Osnet. I live in a little private road called Cypress Place, and I don't always have wine with my neighbors out by our switchboard, but I have been more recently because there have been some builds happening on our little private road. And as those builds have begun, we have realized that we don't have enough of everything. Not only do we not have enough space, but we also don't have enough capacity for some of the things that these new builds are trying to achieve. So I have had to watch Downer out there at the transformer on the pole, trying to figure out and pull their hair out a little bit, trying to figure out how they can get some more capacity into our street in order to provide some things, not only for electrification, EV chargers, but also with an aging population in our street. Some of these people need elevators, and some of which require three-phase. And unfortunately, if you have a 63 amp service and your elevator requires 70 amps, you're in trouble. So unfortunately for many people on our street, they're finding with electrification, adding EVs, electrifying their homes, or maybe even adding an elevator, they just don't have enough juice. And whilst we get these sometimes on our computer, that's nowhere near as problematic as it happening on the place of your residence. So what I've done at my house with my electrification is I've actually gone through and went, okay, well, can we solve this with other means? And so my electrification journey for electric vehicle charging and electrifying my house was a technology integration. I've got battery storage, solar, EV charging, all working together in a bit of a closed system. And that means I don't need as much power from the street as I would otherwise have needed. I generate it, store it, and dispatch it as I need it required locally. And that, as far as what we do as a business, that we kind of find ourselves in the place where if we can solve this problem through technology integration, through good system integration, modern energy IoT, and some sets of services to go around that, maybe we can solve this also for C&I and utility customers. And of course, that's what we do. Now, as far as our mission, I truly believe that integrated technology is how we're going to enable these energy transformation initiatives. It requires a lot of dynamic skills. To solve this, we need energy management, electrical engineering, power automation, and digital systems all working together. So as far as what we do every day, what I do for work is not too different from what I experience and need at my house, and what the market and what the rest of the country is needing. So it's just a little bit of further need. So start A2EP, you get on this thing, I'm quoting something from the EEC. These are sister organizations, but I highly recommend that for the attendees, you go have a look at the Clean Energy, Clean Demand publication from 2023. I think it will help understand that it's not just about getting clean energy, but it's also about how the demand works. And I think that's just a good principle. So for our attendees, that's certainly a good read. A couple of really simple principles here. Fundamentally, first one is, remember, when we talk about some of these power quality concepts, what we're talking about here is kVARs, kVA, and kilowatts. The classic beer analogy, remember that when we talk about transformer capacity, we're talking about kVA demand, no matter how efficient and effective that power is. So we are talking about the best pour while retaining a little bit of kVARs. And when we're talking about energy and demand, when we're talking about demand, we're not talking about volume here, we're talking about rate. So to that end, just making sure that we understand, we are talking about right now avoiding the size of the engine required to go a certain speed, not necessarily distance traveled. So I hope that that just fundamentally makes sense for anyone who's watching this looking for a metaphor analogy to compare. Now, I want to just talk for the rest of this session, give some examples about a couple principles. First of all, core principle, you can't control what you don't measure. If we want to have any chance of controlling these things or determining what to control and how to resize and how to even interface with essential energy, we need to do measurement. And fundamentally, a tech stack doesn't have to be ours, it's just an example. A tech stack, in order to do that, is essential. No, not there to essential energy, but it is essential to unlocking the energy ecosystem. So our philosophy is you need some things operating at high speed at the edge to manage these real-time demand requirements, but also to, as was mentioned in the previous presentation, to be able to forecast and anticipate what those things are. We want to use modern software, not just ours, there's plenty of other examples out there, to be able to look at the forecast, look at the pricing, connect with other stakeholders to be able to manage the demand at the edge. So you need a tech stack in order to do this. Anyone trying to do this manually, running around with castle keys and breaker switches, it's just not going to work. And thankfully, we don't have to do that in 2025. Technology solves this. So let me give you a couple of quick examples. One, these are all redacted, but they are real examples that are under our management today. First, a shopping center. They were being faced with a large transformer upgrade to put in a new wing of this shopping center. Well, instead, they put a large amount of car park solar and then implemented a demand management system, taking advantage of the building envelope and making sure that the loading and unloading of the chiller management system on site was done in such a way that it could avoid having to upgrade the transformer for those rare times, as the previous presenter showed on the duration curve, that you don't actually need that much capacity. If we could manage it in a shorter, faster amount of time, we can. And that's a great example. So maybe you or your customer is a shopping center. Great example to avoid a large transformer upgrade. Another example, big meat abattoir, constantly adding capacity, wanting to transform, wanting to decarbonize, just didn't have a big enough transformer. So why not install a large amount of solar behind the meter? But because of the variability of load and the forecastability of the solar, needing something to manage that, insert a battery. So for example, on this curve here, you can see a forecast of 1.5 megawatts, but if that jumps up to 2.2 megawatts, what are you going to do instead? Well, you can't rely on your solar because the solar at this exact time dipped, a small cloud came over on that day, and that is exactly where the battery kicked in. So that little blip there on the duration curve that would be right up towards the front on the left side was able to deliver that extra capacity that otherwise would have been required to come from a larger transformer. Great example. Another example, food manufacturing. This is where the introduction of energy efficiency opportunities like variable speed drives to manage starters, well, that actually created some challenges with harmonics, which could then be addressed by active harmonic filters. And the bottom line is the actual amount of challenges that were coming from their own transformers manifesting in voltage sag events was mitigated significantly by, again, installing technology. I'm going to quickly go through this next one. This is an example where we have large-scale chargers. So this is fast chargers in a small location with a small connection. So rather than paying $500,000 to install a larger transformer, why not install some PV, some battery storage, and have that all controlled in such a way that prioritizes the load control and then takes all the secondary benefits like spot market participation, frequency ancillary services, while it's not doing that primary job. But the speed to get those chargers in and to use them was extensive. Also, just another example of that, whilst the battery is not being used for that, it can also be used for things like arbitrage and other things while it's not being used for peak management. And then, of course, actually controlling those chargers, all of those things working together avoided the transformer upgrade. And then the last example, large bus depot in the United States. The government is committed to decarbonizing, transforming all of these buses to electric, and there was just no world in which that was going to be possible without putting some monitoring and real-time controls in. So this is a great example of a limited feeder from the utility there in Washington, D.C., integrating it into a full microgrid with lots of kinds of generation, as was said earlier, hybrid generation. So this has some gas peakers, some solar, some batteries, and some load management of the EV chargers all happening at the same time. Now, that's a lot of EV chargers to control, but again, with technology, that can all be sorted out. So let's take it home. Some nuggets of some things that I hope you learned. First of all, you pay for not only how far you go, the cumulative distance that you've gone with kilowatt hours and energy, but also how fast you go kilowatts to get there, or kVA in a transformer capacity. Power factor directly impacts transformer sizing. That can be addressed. More power quality themes, harmonics, and unbalance can also stress those transformers' capacity and their lifespan. Transformer size at the point of connection is not the only lever for load needs. DERs, as is going to be mentioned by Stace very shortly, can obviously help. We got some examples of that before. Stace is going to talk to us more about that. You can solve most issues with integrated technology. And lastly, solutions.azzo.com maybe is your Obi-Wan Kenobi. So if sometimes to avoid a transformer upgrade, you just need integrated technology. So start it with measurement, find out what's going on, get some good data, and then do measurement today, do controls tomorrow, and then you'll get a win for the planet and a win for your pocket. Thank you.